let's continue.
All right. So Alexey is starting.
So today now I am going to give you a bit more details on how we compare inflationary models and observations. And then maybe we can have some generic discussion on modified gravity or other things. So about cosmology, about the inflationary models, I remind that basically you have a scalar field which has the simple equation of motion. I assume it homogeneous. And the homogeneous scalar field, it has energy, which is the sum of kinetic energy and potential energy, and its pressure is the difference of kinetic energy and potential energy. So basically, as long as the potential energy is larger than the kinetic energy, we do have some kind of inflationary solution. And the usual approximation we have is slow roll approximation, under which we assume that the velocity is approximately minus v prime over 3h. So that basically like some kind of the constant speed of falling down, for example, in the air. And we also assume that 3h squared is approximately a pi g v. Yeah, so like to the right hand side of the Friedmann equation I put just the potential energy, assuming that the kinetic energy is small. And what we discussed yesterday was that we do have two slow roll parameters. Yeah, like we have two slow roll parameters. In principle, yes, if you want to study more, you can go further and introduce next parameters to make sure that it stays small for a long time. But in principle, yes, for simple analysis, we need these two slow roll parameters. And as long as they are small, then basically we do have inflation. Yeah? In principle, parameter eta shows you that the smallness of parameter epsilon doesn't go away fast. Yes, last time I showed a bit like how you can calculate things. Like you can check that indeed the kinetic energy to potential energy is approximately 1/3 epsilon. You can also find out then that the equation of state, which is the pressure over energy density, is approximately like -1 plus 2/3 over epsilon. So basically, yeah, if you have a very small epsilon, you have slow roll, your equation of state is very close to -1, which is basically a cosmological constant, and you have almost like a de Sitter solution. Okay? But since epsilon is always positive, then your W, it can only be a bit more than -1, but cannot be even lower than -1. Which means that the Hubble constant can never grow. The Hubble constant of inflation would decay slowly, but it can never grow. And how it decays, you can also find out, like you can calculate that h dot over h squared is approximately minus epsilon. Yeah, epsilon small means that in one Hubble time, the change of h is kind of small. Yeah. And what else? And then you can also check if neglecting phi double dot here is indeed legitimate. And then you can check that phi double dot over h phi dot is approximately epsilon minus eta. And that's what I have told you already, like, if eta was not small, then it would mean that, yes, phi double dot is not so small, and then the smallness of epsilon would be like violated relatively soon. So that's the basic idea of how inflation goes. And then let us ask ourselves, how can we have enough epochs of inflation? And mostly today I will assume like a very simple model, just mass term. Okay? That model of inflation already contradicts observations, but I don't care. I just take the simple thing, and I can see how it works. And if I take this V, I can substitute it here. And then, yes, I can see that, V prime is very simple to find, like m squared phi. and then I substitute it there, and I can see that that would be like 1 over 4 pi g phi squared, right? If I calculate the epsilon. So which means that the phi must be larger than like 1 over square root of g, which is like something what I can call Planck mass. So basically, yes, I have to use the scalar field larger than the Planck mass, and then it gives me a slow roll approximation. Then the question is from how far away I have to start in order to have at least like 50, 60 e-folds of inflation. That I can estimate also easily, because you remember I told you yesterday that if my universe has expanded like e to the n times, that means I have n e-folds of inflation. How can I estimate how many e-folds I can have? Well, that's kind of simple. That's the change in the natural logarithm of a, just by definition. How can I estimate how my scale factor changes? Of course, it's very simple. I can calculate the integral of h. Why? Because in inflationary solution, the scale factor goes proportionally to exponent of t. So that's how I can calculate the amount of inflation. And then I kind of have my formulas here. Here. So how do I do that? I can say, okay, here I have h, and instead of t, I want to take phi. And you see like d phi is equal to minus v prime over 3h dt. And let me just forget about the minus sign. I can correct it by changing the order of integration, the starting point and the final point. So basically here I will have like 3h d phi over v prime. I'm just trying to estimate the value of the integral, so I don't care about the signs right now. And then it means I have here like 3h squared over v prime d phi, right? And what is 3h squared? That's 8 pi g v. So basically the final result I have, that's 8 pi g, the integral of v over v prime d phi. That's the amount of inflation I can get. I have to integrate from like initial value of phi to final value of phi, to the exit from inflation. And let me, as an example, let me take the inflation on the mass term. So if I substitute it here, what do I get? I get like phi over 2, yeah? So for the mass term inflation, I have it like 4 pi g integral phi d phi. So it's kind of very simple to take this integral. That would be 2 pi g phi squared in the limits from like, you know, final point to initial point. Because initial point is bigger, so I put it there, and that's because I didn't change the sign here. So anyway, I just estimate the value, and now let me just neglect the final value. So basically, I have to start the inflation. I have to start the inflation from the value which is given like by square root of n over 2 pi g. So that's the starting point I need. And, you know, I can also write it like square root of n over 2 pi Planck mass. So that shows how much I have start like higher than Planck mass. If it's that guy is like, you know, around 60, this guy is around 6, it's like square root of around 10, which is like around 3. So basically I have to start like a few times higher than the Planck mass, and that's enough. I can get 60 force of inflation. So that's kind of very simple. I mean, yes, it can be worrisome for some people if you have the scalar field which has values above the Planck mass for the quantum corrections and things like that. But actually, if you compare with the observations, then you can see that the mass then should be like 10 to minus 6 Planck mass, which means that if I start from just a few times higher than Planck mass, the energy density here is quite below the Planck energy density. So at least it's not like definitely problematic for me, even though yes, you can worry about quantum corrections, but usually we don't care about anything if we study inflationary models. So, okay, that's one thing. Now, another thing, let me just prepare some simple numbers I will need. Let's assume, okay, as I also told you, basically if I need like 50, 60 e-folds of inflation to solve my initial data problem, it means that nowadays the longest wavelength I can observe in the CMB sky, the longest wavelength is basically like something which was like exiting the Hubble, the Hubble scale region, some like 50 e-folds before the end of inflation. So basically to compare with observations, I have to understand what kind of small slow roll parameters I had, like some 50 folds before the end of inflation. So that's kind of easy to see. Let me take like epsilon. I have like 1 over 16 pi g. Then v prime over v. Okay, I erased the v prime and v, but you remember v was m squared phi squared over 2. V prime therefore m squared phi. And that means I have like 4 over phi squared here. Yeah. And eta is actually the same. V double prime over v is 2 over phi squared, so for this mass term inflation, epsilon and eta just equal to each other. And both of them are kind of 1 over 4 p g phi squared. And I see that 50 folds before the end of inflation, I need this value of phi, so which gives me like 2 pi g over 4 pi g n, which means I have like 1 over 2n. So if I take 50 folds of inflation, it means that my slow roll parameter was like 0.01. And this one also the same. Okay? So that's something I will need later. If I take the mass term inflation, I look at 50 folds before the end of inflation, both slow roll parameters are equal to 1 in 100. Yeah? 0.01. Okay, that's some simple numbers I will use later. And then the next thing is like, how do we predict perturbations from inflation? That's something for what I didn't have much time yesterday. So we are doing some quantization of fields. On one hand, the level at which we are doing quantum field theory here is very simple. I just looked for small perturbations around the background solution. I have basically quadratic action, I have linear equations of motion. Basically, I'm quantizing free fields. So there is nothing difficult about that. Even if I'm quantizing gravitational waves, I don't care then about full quantum gravity. I just quantize linearized equations for gravitational waves. So I'm just quantizing free fields. That's kind of simple thing. On the other hand, yes, behind that is the idea of whether I should quantize gravitational field and how. And also, even for scalar field, that's basically quantum field theory in an expanding universe. Like it's not a Minkowski space-time. So that's another problem. Like how do I understand quantum field theory in a curved space-time? But I would not care about anything. I just go and I look at the de Sitter space-time, and you know this thing here. It assumes that I use the physical time. Now I want to change to conformal time, in which the metric would look like that. And if I want to use conformal time for de Sitter space-time, I can do that by assuming the scale factor going like that, with time going from minus infinity to 0. Like 0 time is now the infinite future. And this h is basically the Hubble constant in the usual like physical time, the usual notion of the Hubble constant. For example, if I want to calculate what I call like curly h, a dot over a in the conformal time, then you can see that obviously I get like 1 over tau, yes, so 1 over t. 1 over t. Which means, yes, as usual, I got it like h multiplied by a. So, yeah. And I want to do quantization here in this space time. And also, as we discussed yesterday, you can find out that the quadratic action for gravitational waves looks very simple. Very simple, but it has, you know, this prefactor which depends on time. And then you have like hij dot squared minus the gradient squared. You have this action for the gravitational waves. That we kind of guessed from the way the equation of motion for gravitational waves looked like in the perturbation of the Einstein tensor. But actually, it's not so difficult to derive like even at the level of the action. You can take the Einstein Hilbert action, you can substitute this kind of metric plus small perturbation here around Minkowski. And since hij is traceless and transverse, not so many terms survive. So you can really derive this quadratic action around expanding universe quite easily. And then what we do a change of variables. Oh, and sorry, here was not 1/2. Here was like 64 pi j. And we can change the variables like hij. You remember it has like 2 polarizations. So in principle I can take like square root of 32 pi g, and then I can put here like the first mode over A, and then the polarization tensor, and then the second mode over A, and then another polarization tensor. Just 2 different polarizations. What I do here, I change the prefactor so that I want to have the canonically normalized kinetic term with 1/2, and I'm keying this A by this guy here. So if A was constant, and that's basically what I get, let's forget about 2 polarizations, I just take one of them, and after all I will just multiply by 2 the results. I have the action like this: V dot squared minus gradient V squared, and it would be all the thing if A was constant, but since it's not constant, I get kind of, you know, time-dependent mass term, like that. So that's the action which I want to quantize, and that's very similar to what Shamit Das was discussing like in the first lecture. You have, you know, some kind of time dependence here. You want to quantize. You immediately have the questions of what kind of vacuum you have, with Bogoliubov transformations and things like that. And also, as I mentioned last time, in cosmology, what we do, we just, you know, think that, okay, in principle, how this, you know, the Sitter universe is done is that you have some, you do have some kind of curvature scale, which is like inverse Hubble scale, inverse Hubble constant. And during inflation, it's almost de Sitter, so that's like kind of almost constant. It's basically constant curvature scale. And you have your scale factor which grows. And of course, all the waves, they grow in length. So basically, every perturbation, it has its length which grows fast, which becomes much larger than the curvature scale.
But at some time in the past, it was very, very small, very tiny. It was like living like, like in Minkowski space-time. So the idea of the Bunch-Davis vacuum was that, okay, let's assume that in the far past, it was basically the usual vacuum of Minkowski. And then look how it evolves. I mean, people can play different games around that, but that's the simplest idea which you can do, and which is always done for these predictions. And basically, then you go and say, okay, I want to study the behavior of the plane waves. I have this mass term. This mass term looks like 2 over t squared. So like find the past, the mass was 0. Yes, indeed, the gravitational wave did not feel the universe expansion. So basically, what you want to have that in find the past, you have the time mode here going like this with k just modulus of spatial k. So that's what you want to get. And you can look at the equation of motion, and basically you can check that the equation of motion you can actually solve like vk of t going like that here, and then plus like that. So you can solve the equation of motion for this strange oscillator here. So then, my infinite past is t going to minus infinity. So this term just dies out. You have the usual plane wave in Minkowski space-time. And as time approaches 0, you remember 0 was like infinite future. The mode goes to infinity proportional to a, which is not surprising just because, how I got this v, I was multiplying h by a. So yes, I get this in the behavior of this thing. And then yes, I want to predict what kind of minimal quantum fluctuations I must have there. And then the calculation I can do I can try to find out the vacuum expectation value of the square of the operator of my field. I mean, it makes no sense to just go without square because it would be 0, of course. The typical value of v squared gives me like some kind of typical fluctuation up or down. And as I told yesterday also, it would be better to take like separated like vx plus vy, or vx vy plus vy vx, and estimate what I get here. And then after that I can take the limit of x and y going together. And you can do the things which Adi was doing a lot in his lectures. And then finally you will find out something like the following. Like d cube k over 2 pi cube over 2k, and then vk modulus squared, this mode which I found there. In Minkowski it would have been just 1. And then multiplied by cosine, let's say r cosine theta. And here I have to say how I introduced I introduced here the spherical coordinates in such a way that, like, I have here x, I have here y, I have the vector from x to y. Let's say that this vector has the length r, and then if I have some wave number, I introduce here this angle as theta, and phi would go just around that picture. So that's why. And here, like, if I do these calculations, I have, like, scalar products of k to x minus y and y minus x. They are symmetrized, that's why it's cosine. And here is, like, kr is basically the multiplication of the length of the vectors and cosine theta between them. So basically, I get that. Then of course, I have to remember that d cube k is basically k squared dk sine theta d theta and then d phi. And then if I have in my integration, I have sine theta d theta and also cosine kr cosine theta, I can change the variables to d alpha cosine kr alpha, right? Simple change of variables. Alpha is cosine theta, so. And after that, of course, it's not so difficult to take the integration with respect to alpha. And then basically, yes, if you do accurately all the calculations, you get the final result. And what else? What else? And I also need to find out what is this guy here. And that's kind of very simple. And let me now look at these results in the limit of time going to 0. I won't like to look in the future. What happens in the future? What happens in the future? It means that my v squared here, it goes to 1 over k squared t squared, right? And 1 over t squared, I can find out it like a squared h squared, just from the equation there. So that gives me a squared h squared over k squared. That's the limit to which v goes. So basically, yes, my idea is that all these, perturbations, all these fluctuations, quantum fluctuations, they were born in the past, and they were of very small wavelength. And now I'm looking at what kind of result I get as time passes. And it goes like to this limit of t equal to 0. And so if you substitute all of that, basically what you get a funny result. You get like dk over k, then sinus kr over kr, and then you get, let me check my notes so that I don't confuse some coefficients, and you get here h squared a squared over 2 pi squared. So I have here some kind of measure which goes like the same with all the scales. Here I have the guy which is from the separation of 2 points, and that goes to 1 if I take r to 0. And this guy is what would be called like power of these fluctuations for v. Of course, the thing diverges both ultraviolet and infrared. In ultraviolet, that's kind of obvious. That's always like what we have in QFT, because we go to smaller and smaller scales and we get like larger and larger fluctuations anyway. So that's kind of natural. Why it converges in infrared? That's because I have this k squared also here, and that's the problem of the sitter, because it has like all the same at all the scales. And if I choose one point in my de sitter for any wavelength, I can trace this wavelength back to some infinite past in which it was infinitely small wavelength, and therefore all these fluctuations. So basically in the sitter, if you wait for enough time after the sitter was born, you get the fluctuations from all the possible scales. Yeah. So that's the usual story why people think that the sitter might be not good enough for quantum field theory and things like that. But for us it doesn't matter. Okay, we just assume that we can trust this prediction, and that's what I get. In a sense, it's not like a big deal of quantum field theory what I get here. In a sense, you can look at this Hubble horizon scale as some kind of measuring device, because after that, one of the modes stays constant. So your Hubble horizon is like a measuring device, and then you do measurement. So you basically can look at this quantum field, and then you want to understand its amplitude when it reaches this size of the Hubble scale, h minus 1. Yeah, this Hubble size. So you can ask yourself, like, it goes like if you want to localize your quantum field in a box of this kind of size, and then if you think like intuition about quantum mechanics, what does it mean if you want to localize your field in this kind of box? It means that the amplitude of the field would not be precisely determined, and you can imagine that yes, the typical fluctuation of the field would be like inverse of this length scale, which is h. what I get here. So basically that's all we need from quantum field theory for inflationary predictions. Not much. And then, yes, finally, what I want to predict the fluctuations of H, which means that I take delta H squared, I take two polarizations, I go back to this to this normalization, since okay, I have to go like square. Yeah. So from this power spectrum of E, I have to multiply by this prefactor to get power spectrum of H, and then I have to remember I did have two polarizations. So that's the final result for gravitational waves, and what I get here, I mean, very simple. Yeah, I just have to multiply everything by everything. And what I get here, I get 16g h squared over pi. So that's the final prediction for the gravitational waves. If I have some inflationary model, I can calculate what kind of value of h I have, and then I can ask myself if my observations must give me results or not. And one more thing here is that I did that calculation for purely de Sitter, pure de Sitter. But yes, we know that the real inflation, it changes the Hubble constant very slowly, but it changed the Hubble constant. And in principle, yes, since the mode becomes constant after crossing the Hubble scale, basically I have to take the value of h at the time of horizon crossing. At the time of horizon crossing. And then let's look at what happens. Like I have time, and by time I would mean just scale factor. Time goes as the universe expands. And I can draw here the Hubble scale. Yeah? First I have inflation, and the Hubble scale is almost constant, and then becomes growing faster than any kind of linear function. And I have some wavelength, let's say lambda 1 here. I have some another wavelength, lambda 2. I have yet another, let's say lambda 0, and so on. Okay? So every mode, it was born at very small wavelength, and then initially, during inflation, the curvature scale stays constant, the wavelength grows, and finally the wave goes outside the horizon, and then it has this constant mode, which we can predict without knowing much of the physics, because this huge wavelength that just stays constant. But then the universe ends inflation, becomes to decelerate in its expansion, and then yes, the curvature scale grows fast, and finally, even though my wavelength still continues growing, it grows slower than the curvature scale and comes back to inside our horizon, and we can observe that. Yeah. So, and the longer wavelength exited the horizon during inflation before the shorter one, right? So that means that the longer wavelength, it corresponds to earlier values of h, which means to higher values of h during inflation, which gives me the rectitude of gravitational perturbations with inflation. And maybe the last thing I'm going to do now about this topic is to estimate the tilt. That's very simple, so I want to show you how it goes. By definition, the tensorial tilt here is like double logarithmic derivative of this power spectrum with respect to the wave number. That's just the definition. Then how to calculate that? If I look at all these waves, then the physical wavelength is basically scale factor over the wave number. I mean, when they exit the horizon, they do have the same wavelength basically, because the Hubble constant does not change much during inflation. So the difference is basically is that if I have different wave numbers here, it means I have different scale factors at the exit from inflation. And if I want to calculate the variation of the logarithm of the scale factor of the wave number, that's basically the variation of the logarithm of A, and then which basically means h delta t, right? Which basically means minus 8 pi g v over v prime delta phi. The same way how I was calculating the number equals. Change of time corresponds to change of vector of the scalar field phi. On the other hand, the variation of this power spectrum, all the coefficients here are constant. So it means that it's just two times variation of the logarithm of h. Oh, okay, let's say just logarithm of h squared. And how do I calculate that? 3h squared is equal to 8 pi g v, energy of the scalar field. So that's the same as the variation of the logarithm of v, which basically means that that's variation of v over v, which means that that's v prime over v delta phi. So very simple calculation of what does it mean to make some small variation of the wave number here, exiting the, yeah, because if I change the wave number, it means I change, like, you know, the time of exiting the curvature scale, and the change in this guy here is the change of h. And then I just have to divide one by another, and you can see that here is 8 pg, and basically what I get epsilon with minus sign from here, and, you know, change in a coefficient like that. It's minus 2 epsilon. So that's it, that's the answer. And because all of those guys were like 0.01, it means that if we manage to register the gravitational waves from the master inflation, that would give us, like, you know, this kind of redshift. Okay, and I'm not going to discuss how to do the same for the scalars, but actually for the scalars it's even a bit easier. You can in principle, in a slow roll approximation, it's just enough to quantize the fluctuations of the inflaton field itself, which go basically almost the same way, because you can neglect the mass of the scalar field for these perturbations. And then the only question is how to predict the fluctuations in the Newtonian potentials if you had the scalar field fluctuations. And the point is that, as I also mentioned some time ago, if you can define this kind of variable for perturbations where u is the velocity of the scalar field of your fluid, which here would mean like what does it mean? Yeah, it would mean like h delta phi over phi dot. So basically you need to calculate this variable. And then you can also go for finding the quadratic action, or you can try to study the perturbations of the scalar quantities and try to figure out what kind of natural variable is there. And this approach you can find in the textbook of Slava Mukhanov about physical foundations of cosmology. But finally, you can find out that the variable you want to quantize is a so-called Mukhanov-Sasaki variable. And Mukhanov-Sasaki variable is, okay, let me also, let's say like U, big U. Mukhanov-Sasaki variable is A delta phi plus psi phi dot over what? Over h. So basically, yes, again, the same way as we went for gravitational waves, we have to, to take care of this, prefactor in the action from the metric. And if you have slow roll condition and phi dot is small and less, basically you quantize the scalar field itself, the inflaton field. but yes, if you want to be accurate, you can quantize this variable. And finally, yes, because you want to quantize delta phi, and then you want to calculate r, you will have to multiply by h and phi dot, the whole result. And basically the final answer is that here it would be like h squared over 2 pi phi dot squared. That's your scalar perturbations. I mean, the action for this guy would be very similar to the action for the guy V, just the mass term will be a little bit different. But in the slower approximation, even the mass term will be the same as here. So the quantization would go the same way like I discussed now, and you can predict then this guy. And you know, the difference here is that phi dot goes to the denominator precisely because this correction here was small for the Mukhanov-Sasaki variable, and that goes like enhanced when it goes to calculation of the Newtonian potential. And here again, here there is some kind of funny historical thing that the analogous double logarithmic derivative here is called spectral tilt -1. So like spectral tilt for gravitational waves, if it's flat, it's 0. For scalar fields, if it's flat, it's 1. It's just some historical, convention, which makes no sense. And here I could also derive very simple how I can calculate the spectral tilt. And here I would also get eta because I also have change in phi dot. And I will have here, let me see what I have here, like 2 eta minus 6 epsilon, which would give me like minus 0.04, which means the scalar spectral index 0.96. That's perfect for observations of the CMB. What is worse is that finally now I was able to find like the amplitude of perturbations here for the scalar fluctuations. I have measured them in CMB, of course, so I can find out what kind of amplitude it was here. And then I can ask myself, what kind of amplitude must then be in the tensors? And this guy, like tensor to scalar ratio, it's very simple to calculate. You just take this guy here, you divide by that guy here, and then you have phi dot, you have h. Yeah, phi dot you find like v prime, h you find like v, of course. And like after 1 minute of calculations, you can see that here you will get 1 over pi g v prime over v squared, which means 16 epsilon. And that means that for mass term inflation it's 0.16. It means that if you found some fluctuations like of the square of amplitude in fluctuations of the scalar modes, then you also must have something in the tensor modes, which with the square like 16% of the square which was like in the scalar ones. And that's something which we do not see. Now we know for sure that it's less than 0.1, for example. So that's a problem of this chaotic inflation. Now they contradict observations. So and also it's very obvious to see what should you do to not contradict. Yeah, you want that the tensor modes are much less compared to scalar ones, or another way around. You want the scalar modes are much higher than the tensor ones. You need even smaller phi dot here. So you need like even stronger slow roll condition, which means that instead of phi squared, you can go for inflation like that, potential going to the plateau. Then of course the slow roll is even better satisfied, like in Starobinsky inflation, and then you don't contradict the observations. Okay, so that was just some picture to give you how we predict fluctuations from inflationary models. How we say that some inflationary models are now ruled out and some of them are good. So that's the basic idea of how we do that. Okay. Then I still have like 15 more minutes. So now I would like just to have some general discussion with you, because I mean somehow we want to modify gravity very often. Why is that? There are different reasons. I mean, on one hand, we want to do like cosmology better because I already mentioned like small scale structure problems, H0 tension. We do have something there. In principle, maybe it's not like the best motivation to do modified gravity because if it's just about H0 tension, the Hubble constant value now, what you want to do, you want to change the expansion law of the universe. And to change expansion law in the late universe, it's kind of quite simple. Whatever modification of gravity you have, you just do that and you get some results. But almost for sure, you just destroy something else. Because yes, you change the expansion law, you might be able to give the good value of the Hubble constant now, but you also change some intermediate scales, and then you change the formation of structure like baryon acoustic oscillations, and then nothing good you have. Another motivation for modifying gravity is like quantum gravity, which is also a funny point, but I think actually that maybe we also have to understand quantum field theory better, precisely about gravity. And some people are trying actually to have quantum gravity from some non-perturbative things, like loop quantum gravity, for example. They are doing this kind of things. Still some 10 minutes.
Yeah, I'm 10 minutes more.
So,
No, I'm just thinking about how we time this.
okay.
Not you, anyway.
Okay. So, and I would say actually that quantum gravity probably should not be normalizable in principle. Because, what is very special about gravity is that kind of the charge for gravity is energy momentum. So like what makes the gravitational interaction act is the energy and momentum. So basically the idea is that the higher energy you have at your hands, the stronger like cross sections, the biggest cross sections you get, and that's the property of gravity itself. It depends on the energy and momentum in this way. I mean, so that doesn't speak in favor of normalizability, I would say. I mean, you might think that probably yes, we need to change gravity because of that, but I think it's just our problem that we are not able to work the quantum fields non-perturbatively. And also, in my opinion, much more than this kind of technical issues, much more important is that we also have some conceptual issues. Like for quantum theory, we need to know time. We need time to be something special. We want to have this unitary evolution and everything. And that's not what we have in GR. Just very different philosophy behind. So maybe it's a problem of philosophy. But anyway, so nowadays we have lots of different motivations, not always very good motivations to modify gravity, and we are doing that. And actually it turns out to be very difficult. And that, since it's very difficult and usually you modify gravity and destroy everything, that's why it's even more interesting to modify gravity. So, I mean, at least for me, personally, for me it's interesting because I want to understand how it works and why I cannot do some things and stories like that. And let me just give you in a few minutes, some overview of lots of different approaches to modify gravity. For example, like, you remember, the action principle for gravity is this Einstein-Hilbert action, scalar curvature. What's special about that is that, yes, it does have this problem of second derivatives inside it, which don't influence equations of motion because they're just a boundary term. But if you want to go and modify gravity like that, like f of r gravity, then you immediately get higher derivatives here in its equations of motion. That's not bad for f of r because you can do some funny trick. You can say like, I introduce some extra field, phi, do it something like that, and then, was it correct? Or maybe I have to do it like this. And then yes, if your f double prime is not equal to 0, you make variation with respect to phi, and you get equation of motion which tells you phi equal to r, substitute back and you get f of r. So you can rewrite this kind of models like in a scalar tensor representation. And basically, yes, these extra high derivatives give you just one more scalar mode, and that's actually kind of funny playground, more or less simple. And like the classical thing is the action like that: r plus r squared That's what is called Starobinsky inflation. Now he sells that as if he invented inflation before other people, which is not precisely true. Because if you look at his paper of 1979, he indeed took this kind of model, but the paper was called something like no initial singularity in cosmology. So he did not have kind of physical ideas about inflation. He just found non-singular solution here. And why it was actually? It was because, if you go to the scalar tensor representation, the scalar field has the potential which goes to plateau here. So if you take one particular trajectory, which in the past asymptotes to infinite value of scalar field with zero velocity, it basically asymptotes back to cosmological constant. And the cosmological constant gives a de Sitter space-time. It's free of energy, free of singularity, but only because you have chosen one particular trajectory there. So that was a very funny paper. And yes, nowadays it's basically the most successful inflationary model because it predicts very small tensor to scalar ratio, like 10 to minus 3, I think. So it does not contradict observations now. But to claim that he was the first one that was inflation indeed, it's a bit like of cheating, but it was interesting. And then you can go that's only for fun. If you go to nonlinear corrections like Ricci tensor squared, this guy does have ghosts. The modes which have negative kinetic energy. And that's bad. That's absolutely bad for quantum field theory, but even in classical physics, negative kinetic energy is nothing good. Because basically the problem starts like at the G-level diagrams. It's not about quantization. So you don't have any kind of stable vacuum. And sometimes you might have, some kind of potential energy instability, and then you would have some kind of time development. You would have some time scale of instability, and you can, control that. But if you have some kind of instability in kinetic energy, there is no time scale. You go to smaller wavelength, you get higher frequencies, and the instability goes as fast as you want. So there is just no time scale with this kind of instability, so that's a problem. Another idea in these things here is that you can try to take the connection coefficient as an independent variable to have some kind of Palatini variation, what they call. And then yes, you can go even further. You can try go these kind of models and these models. And like in FFR, it doesn't give you integers of freedom, for example. It gives you some kind of scalar there. I would say people still do not quite know very much about that. They use it a lot, but foundationally, I'm not precisely sure if everything is all right there. But that's some kind of open question, we say. Then one more idea sometimes is just let's make the graviton massive. And you know that to make the graviton massive, you have to kill the gauge invariance. And after you kill the gauge invariance, as I mentioned on one of previous days, you immediately get ghosts. You immediately get negative kinetic energy modes. And basically, what was known to Fitz and Pauli is that if you manage to find this kind of Lagrangian for perturbations around Minkowski space-time, then this kind of Lagrangian still has one constraint there, even though not first class and second class, so it produces another constraint there. But then yes, you don't have ghosts. You have like ghost-free massive gravity at the linear level. But then you go to higher orders, you get your ghost back. And what people found some 10 years ago is that you can take this kind of Minkowski metric as the background. You take the inverse of your physical metric, so you need to have two different metrics. You multiply like one function by another function. You get some kind of square matrix here, and you take square root of this matrix. In a sense, we find the matrix which multiplied by itself gives you that matrix. And you take trace. And that's the simplest potential you can have there to not have a ghost. That's kind of quite quite strange guy here to use. So yes, now they were constructing theories like that, and then it appeared that it's almost impossible to construct cosmological solutions. You have to modify even more to make, for example, both metrics dynamical or introduce yet another degree of freedom there. So lots of things. And then many people now go for studying some some models which have second-order equations of motion by some chance, like if you take Lagrangian like that, it still has second-order equations of motion, and that's what called Galilean fields. Coming back to the 70s by Krondesky, but then they were rediscovered some 30, 40 years later, and only later people realized that the discovery was basically a particular case of Krondesky. And if you want to try these games, you go like construct hundreds of possible models for scalars, analogously for vectors, and then you can go beyond Krondesky, asking yourself, okay, maybe I do have higher derivatives in my equations of motion, like for FFR, but they can be removed by change of variables, and the model is healthy. So then they go also that way. And I can also mention one more thing, is that in principle, yes, I restricted myself to Levi-Civita connection, but you can also go for other connections with torsional metricity. And basically every such connection you can write like Levi-Civita plus some combination, let's say, of torsion tensors. And then you go for Riemann tensor. And the Riemann tensor is basically like Levi-Civitian Riemann tensor plus some combination of Levi-Civita covariant derivatives plus quadratic contribution from here. Why is that? Because the Ricci tensor is kind of like delta gamma plus gamma gamma, right? So you can do this variation and get something like this. And for example, yes, you can find some kind of torsion theory which doesn't have curvature, doesn't have metricity, but it has torsion. And you can find, one particular Lagrangian which would be like equivalent to the Einstein-Hilbert Lagrangian modulo some surface term which you don't care about, and that's how you get teleparallel gravity if you go for torsion. You can do the same for non-metricity and get like symmetric teleparallel gravity. And then you can try to modify this kind of gravity, which was equivalent to GR, by going for some nonlinear functions like here, and then you get neutrons. Like you don't get a well-defined number of degrees of freedom and things like that. So yes, that was all my time basically. So yes, I tried just in several words, like in 15 minutes, to overview basically not precisely the details, but just to show you that there are like hundreds of possible ideas for modifying gravity. Almost none of that works well, and that makes it even more interesting to study that. So yes, that was my message from the second part of today's talk. Yeah, that's it.
Yeah, thanks, Alexey. Any questions?
Do FR theories have anything to do with dark matter observation?
I mean, of course, you can also try to study some kind of modified gravity for dark matter. People do it in different things. Some people try to find some FFR function which gives you something like rotation curves in galaxies. Some people can also try biometric gravity from massive gravity. After that, you have like one massless graviton and one massive graviton, and they are trying to use a massive graviton for dark matter. So they are also doing that. And of course, there was this kind of crazy story about Mond, and you just try to modify like already at the level of the Newtonian mechanics. But then, of course, you need to find also relativistic extension to that. And then, it's again a story of being difficult to modify gravity. Because if you just go like looking for simplest way, you add some new scalar field with some non-canonical kinetic term, some k-essence scalar field. But then after that, you don't produce the correct gravitational lensing because the photons don't really feel the scalar field. And then after that, yes, you go to some tensor vector scalar mode. You can do that, and then people are trying to do some cosmological models like in this TVS stuff, reproducing Mond. But then, yes, even after, okay, you still have to add a bit of some kind of massive neutrinos for some kind of dark matter, because once you solve the problem at the scale of the galaxies, Mond doesn't solve that at the scale of galaxy clusters already, so you need some modifications there. And even after all the modifications, they fail to reproduce the third peak in CMB. So it's not so simple to reproduce everything by just...
they produce it now with this Armand, but then it has these... Remember when you talked about it?
the one which was...
these Czech guys. Remember this Armand, they produced it, but there was another paper saying the Green's function was,
yes.
like in between oscillations. Like the stuff I was showing in the morning.
Yes,
so
yes, I forgot
highly
about this.
problematic.
So yeah, sometimes you can, you can always go like one more step. You get some new problem, you get one more step, and then you create some huge model, which also has very strange properties inside. So yeah.
Any more questions?